sum and integral representation for beta function. Okay, so in this video we will look at why both of these are true. Now first one is actually the definition, so I'm not really going to say why this is true, because a definition is a definition. Yeah, so we know that beta function of s is defined in this way: 1 by 1 to the power s minus 1 by 3 to the power s plus 1 by 5 to the power s minus 1 by 7 to the power s and plus 1 by 9 to the power s, and so on. This sum cannot be really found out using the zeta function, so that's why this is defined as its own sum in a new with a new variable beta. Yes. Now okay, so this sum, if we write it in terms of summation notation, will just be this one over here. Yeah, because the first has positive sign and it's negative sign, so we have minus 1 to the power n, and 2n plus 1 just gives the odd term. Yeah, so this summation notation is just trivial. Now from this summation notation, let's try to get this integral representation. Okay, now what I'm going to do is I will just use the inverse Mellin transform of this expression. 1 by 2n plus 1 to the power s. What I will do is I can write 1 by gamma s and then gamma s by 2n plus 1 to the power s. Yes, okay, I will write it like this. Now if I take the Mellin transform of this expression, sum from n equals to 0 to infinity and then minus 1 to the power n by gamma of s. Now this is integral from 0 to infinity. This will just be x to the power s minus 1 and then e to the power minus of 2n plus 1 times s and dx. Yes. Okay, wait, not really s over here, it should be x. Sorry for that. This should be x. Okay, so e to the power minus 2n plus 1 times x and x to the power s minus 1. So this, if you just evaluate this integral using the gamma function or Laplace transform or Mellin transform, you are going to get this result. So I'm doing it. Now after this, let's interest in the sum and integral. If you're interested in the sum and integral, we are gonna get integral from 0 to infinity and then sum from n equals to 0 to infinity of minus 1 to the power n by gamma of s, x to the power s minus 1, e to the power minus 2n plus 1 times x dx. Now let's just write the expression that are in the world of n. Let's take order outside the sum because they are just constant for the world of n. Yeah, so 1 by gamma of s, yeah, and then x to the power s minus 1, and now sum from n equals to 0 to infinity. Also e to the power minus x won't matter, and then minus 1 to the power n and e to the power minus 2nx dx. Yes. Okay, now after this, what I can do is, this is integral from 0 to infinity and x to the power s minus 1 e to the power minus x by gamma of s. Yes, now if we sum this up, this is actually sum from n equals to 0 to infinity of minus e to the power minus 2x to the power n dx. Yes, now this is just a common ratio, and we know that its magnitude is less than 1 because e to the power negative power is there. Yeah, and now we know that the sum of a geometric series is a by 1 minus r. A is just 1, ratio is just this thing, so we can find its sum. This will be integral from 0 to infinity x to the power s minus 1 e to the power minus x by gamma of s, and then this is a by 1 minus will be plus, and then r e to the power minus 2x. Yes, dx. Good. Now if we take 1 by gamma of s outside, this will be integral from 0 to infinity and x to the power s minus 1. If you multiply this by e to the power x in numerator and denominator, this will cancel out. In denominator we will have e to the power x plus e to the power minus x dx. Yes, and this is exactly the thing that I had shown you in the beginning, the integral representation for the beta of s. Using this integral representation, we can also get other identities of beta function that can help us to evaluate beta. Like, let's say what you can do is you can also change this integral representation to logs, and then like get other ways you can get that integral and maybe to find the value. So yeah, this integral can be helpful, because if you can just put s is equals to 2 and then solve the integral and get the value, maybe put s equals to 1 and then solve and get pi by 4 as beta of 1, and then again put x as 3 and get the answer as, let's say, pi cubed by 32. Yes, so yeah, this integral will be really helpful, and this is the way how we get this integral. Yes, first of all, place the Mellin transform and then do the sums. Yeah, nothing more. So this was it. Hope you enjoyed the video. Now I'm pretty sure you know both the integral representation and the sum representation for beta function. Hope you enjoyed the video. Look forward to seeing in the upcoming videos too.